Assalamu alaikum. So, inshallah, today we'll finish with the last type of transforms in this chapter, which was called the Hu transform. And if you remember last time, we have said that this type of transform is a special type in which we use it in order to identify some shapes. So the simplest shape that we want to identify here is the existence of straight lines in our image, right? So here we have said that in order to identify whether a certain pixel falls in the same line as another pixel, actually both of the two pixels should satisfy this equation. Okay? So for example, if I want to say that here, I have the point N1, N1, and N2, N2, right? So here in this case, what will happen is that, how can I say that these 2 points reside in the same straight line if both of these 2 points satisfy this equation with the same rho and same theta? Okay? So for a certain rho and a certain theta, actually this equation is satisfied for both of these 2 points. So in this case, I can say that these 2 points, they fall on this line. What are the characteristics of this line? The line is at a perpendicular distance from the origin with the value rho, and this line that is drawn from the origin to the line perpendicular to it, it makes an angle theta in the positive clockwise direction. Okay? Right? So, if you remember last time, we have proved that this equation is satisfied for all of the points that fall on this line that has the rho and theta values. Okay? But how can I make use of this? How can I make use of this to identify whether, for example, I have a certain pixel or a number of pixels, they fall in the same straight line or not? So, if you remember last time, we have said that I will start with my image. Okay? I will convert it into grayscale. Right? Then after that, from this grayscale, I will try to identify or try to detect the edges that exist in this grayscale image. Okay? So as a result of this, I will have an image in which we only have just edges. Like this one, for example. Let's take this simple image. Okay? Here I have this image. As you can see, I have just a white rectangle in the middle, and the rest of the image, for example, here, as you can see, is black. Okay? So from this image, I will detect the edges. So I will have these edges, as you can see. Right? Then after that, I will apply my algorithm. I will apply my transform of the Hu transform on this edge image. Right? As you can see here, these white lines, they represent an edge between a region of a certain intensity and another region that has a different intensity. The difference between the intensity is a considerable value. So in this case, actually, this edge represents the difference of intensity between the black and white. Okay? So these are the edges. Okay? Right. What is the next step here? Once I have this image that contains the edges of the shape that we have, I will look at the points that correspond to these edges, okay, which are the pixels that correspond to this white values. Okay, where are the locations of these pixels? I want to get the value of n and the value of n for each one of these white pixels. Okay, and I will substitute it in this equation of the straight line that we have seen before, which is rho is equal to n cosine theta plus n sine theta. Okay, and I will have something like this, in which we have the horizontal axis that represents the angle theta, and this angle theta actually it ranges from negative 90 to positive 90 degrees. Okay, and the vertical axis here it represents the rho. In this case, actually, I don't want to draw a curve, rather than providing here, since I'm using discrete values, right? So here I will divide this area in the form of something that are called accumulator cells. Something that are called accumulator cells. So these accumulator cells, actually, in each one of these accumulator cells, I have a counter. Okay? Right. Let's see here. What is the how this algorithm will pass through. So actually, let's consider that this line here, I will have my rho. Let's assume actually the origin is at the top left, okay? But here for simplicity, since I will not be able to reach the top left corner, so I will consider that this is my origin, something like this. Okay? This is the value of rho, right? And this is the end. Okay? Then after that, what I expect to have here is that when I substitute for the value of theta, for the value of m and n for all of these points, they should give me the same rho and the same theta. Okay? Right? So here, what will happen is the following. Now, for all of the values of the theta, okay, for each one of these points, I will compute this relationship. Okay? So here, as you can see, the value of theta, as we have said before, it ranges from negative 90 degrees to positive 90 degrees. Okay? What is the next step here? The next step here, I will take, let's say, this point. And for this point that has the coordinates m and n, I will substitute the value of theta starting from negative 90 to positive 90. Okay? And for each value of rho, actually here, I will see what is its corresponding accumulator cell here, and I will increment it with 1. Again, here as you can see, I have, this is my edge image, okay? So this is my start, okay? What I'm interested in here is the white pixels. So for each one of these white pixels, I will get its coordinates, m and n. M is the number of the row, and n is the number of the column. Okay? And here, the transform will happen as follows. I will use this equation, which is rho is equal to m cosine theta plus n sine theta. Okay? And I will assume that this is my who space. Right? Here I have, this is my horizontal axis is the theta, starts from negative 90 to positive 90, and the vertical axis here is rho. Right? Okay? Right. So here, what will happen is the following, is that this space of theta and rho will be divided in the form of, let's say, small squares, which we call it accumulator cells. Okay? And what will happen is the following. For each white pixel that I have here in this image, I will substitute for the different values of theta, starting from negative 90 up to positive 90. And for each value of theta, I will get the value of rho that corresponds to it. Okay? I will situate the value of theta, let's say this is the theta that I have substituted here. It has resulted in a rho of this value. So I will go to this accumulator cell and I will add 1. Okay? So this means that this point, for this value of theta, it contributes with a value of plus 1 for this value of rho. Okay? Right. Now let's consider the following. Of course, I will apply the values of theta as we have said before for each one of these white pixels for all of the value of thetas that we have here. Okay? When I finish with this point, I will take another point. Let's say, مثلا here, M2, N2. Okay? And for this M2, N2, I will substitute for all of the value of theta from negative 90 up to positive 90. And for each value of theta as well, I should see what is the corresponding value of rho. For example, this is the accumulator cell that corresponds to this theta with this rho. I will add 1. Okay? If these 2 points appear on the same straight line, okay, I am sure that at a certain point, these 2 points will contribute for a certain rho and theta with plus 1. So this means that for the same accumulator cell that corresponds for the rho and theta for this straight line, both of these 2 points actually they will accumulate with an increment of plus 1. صح? All of the points, let's say correspond this, let's say that this is rho 1, this is theta 1. Let's assume that this is rho 1 and this is theta 1. So here I am expecting that all of the points that exist on this straight line, they will contribute with an increment of plus 1 in this cell. Why? Because actually they are residing on the same straight line. And this straight line is represented by this rho and this theta. Clear? Yes?
What's the relation between the relation is they are the same accumulator here for all pixels or?
Yes. Assume that, for example, actually this plotting here is three-dimensional. Okay? So here I have theta, and here I have rho. And for each point of here, actually, I should have a certain integer value, either 0, 1, 2, 3, 4, 5. It depends on how many points of these 5 pixels have contributed to this point.
Each pixel has an accumulator?
Each pixel, it's not, doesn't, here, not each pixel has an accumulator. Here, actually, what will happen is that for this pixel, I will substitute for the values of the different theta from negative 90 to positive 90. Let's say, from negative 90, negative 89, negative 87, and so on, up to 89, positive 90. Okay? And for each value of this theta, actually, I will see what is the corresponding rho. And I will see, for this masalan, let's say for the first theta, the rho has this value. Okay? So here I will add 1. For the theta that comes after it, I found that the rho has this value. So I will add 1. Okay? For the coming theta, for example, I will have the rho has this value. So I will add 1. Okay? So as we can see from here, for each one of these points, okay, I will have a certain accumulator cell here, okay, in which I should add 1 if it satisfies the value of Mn in this equation. Again, things are starting to get clearer. So here the idea is the following, which is that here we have said that for each one of these white pixels, I will get its Mn, okay? And I will substitute it here, M and N. Then after that, the variable in this equation, it will be the value of theta, starting from negative 90 up to positive 90. So I will substitute with negative 90, negative 89, negative 88, and so on, up to, let's say, 87, 88, 89, 90. And for each one of these thetas, actually, I will compute the value of the rho. Yes?
For each pixel, we will substitute the
For each pixel, yes, we will substitute for all of the range of theta.
So M
Yes.
and N are also variables, right?
Yes, but here the value of M and N in this case, for each pixel, they will be constant.
But at least N will change because we're changing the X.
No, actually here I will take it point by point. So for the first point, Mn, and N here does not change for this point. They are the same. I will substitute it here. Then what will change in this equation is the value of theta, from negative 90 to positive 90. For each value of theta, I will see what will be the corresponding value of rho. And see where it is situated here in this map. Okay? Once I find its location, I will go to its accumulator cell here. It is as if something like a container. Each time I have a hit, I will add, let's say, for example, a bit or a coin or something like this. I will increment it by 1. Okay? Then after that, I will see what is the value of rho for the next theta. That is, for example, it is here. So I will increment with 1. And so on. Okay? Until I finish with all of the range of the thetas. I finish with this point. Now I will see the next point. And I will do the same thing. Substitute for the values of theta from negative 90 up to positive 90 and see what will be the corresponding value of the rho. Okay? Fine. Now, as you can see, why for the same point I have different points here in rho and theta? Because actually in this same point, I may have a straight line like this one, a straight line that can pass in this direction, a straight line that can pass in this direction. Okay? So this corresponds to different straight lines that are having different rhos and theta. Right? Okay? So here, what I am trying to do for this specific point, to see what are the possible values for rho and theta. Okay? That corresponds to these different lines with different slopes and different distances from the origin. Okay? Right. For the next point here, on this same line, I will do the same thing. Substitute the value of its coordinates, M2 and N2, let's say, in our equation. And we'll make a variation in the value of theta from negative 90 up to positive 90. And see the corresponding rhos. For each new theta, actually, I will have a new line with a new row. Right? But I am sure that this is one of the lines that passes through this point, and this is the same line that passes in this second point. So I am sure that for the value of rho and theta that correspond to this line, both of these 2 points, they will contribute. They will contribute. Let's assume, for example, that here we have, for this straight line that has the 2 points mn and m2 and 2, it has, let's say, a theta 1 and a rho 1. So its corresponding accumulator cell, it will be incremented once due to the first point, and it will be the same cell, it will be incremented twice due to the second point.
But the second one has different MNN.
Different MNN, but the same rho and theta.
But the value of how?
Because actually you have said that this equation, this is an equation of straight line. Okay? This is an equation of straight line. Where if we have a constant theta and a constant rho, okay, all of the values of m and n that satisfy this equation, this means that they are residing on the same straight line. See what I mean? Somehow puzzling. Right? So here I am transforming from one space to another. Okay? So this means that this straight line, all of the points in this straight line, they will appear as just one point in the rho theta plane. Why? Because this straight line actually it has a fixed rho and a fixed theta. Okay? So this straight line it is represented by one point in the plane of rho and theta. This second straight line as well, since it has a constant distance and a constant theta, is represented by another, let's say, point or a single point in the rho and theta plane. Okay? Clear? But after we finish with all of these white pixels, how can I identify if I have, let's say, straight lines or not? What I should do? I will look for the values of these accumulator cells. The accumulator cell that has the highest value, this means that this is probably a straight line that exists in my image. Okay? So in this case, I can put a threshold. Let's say 100 or 200 or whatever. If the accumulator cell has a value greater than 200, I will consider that here I have a straight line. Okay? So what will happen is that I will see all of these accumulator cells, detect their corresponding values, right? And put a threshold. If I have a value greater than a certain threshold, this means that this point corresponds to a straight line. How can I get the information about this straight line? I know its theta and I know its rho. Okay? But actually I don't know its limits. If I want to know its limits, actually I need to go back to the original image and see from where this edge starts and where it ends. Understand the idea? Okay? So here, what will happen is that if we finish drawing and making the transformation, I can draw the result of the transform in a three-dimensional plot like this one, okay, using either the mesh function or the surface or the surf-L function in MATLAB. Surf-L function or the mesh function. Okay? And as you can see from here, I can figure out where are my straight lines. Here, the first thing that I want you to consider is that this is the theta, and this is the rho, okay? And the vertical direction or the height here, it corresponds to the values that correspond to each accumulator cell. Okay? So as you can see from here, I can figure out where are my straight lines. Okay? So here, for example, here I have a peak. This one is straight line, it's another straight line, it's another straight line. Here there is one which is not clear in this figure, but here we have another peak like this one. Here I have a peak like this one, and so on. Okay? By knowing these peaks and knowing their rho and theta, I can determine where is the position of this straight line in the original image. By knowing the rho and the theta. Okay? Yes, because actually, if we consider that this is my image, if I know the rho and theta, first of all, I will compute. For example, this is the theta. Okay? And we have this is the value of the rho. So the straight line, actually, it will be a straight line that is perpendicular to this rho. So like this, I can determine exactly where is the straight line by knowing the rho and theta. Because as we have said before, the definition of the rho is what? Is the perpendicular distance between the origin and the line. Okay? And the theta, this is the angle that is done by this perpendicular distance with respect to the x-axis. So by knowing the rho and theta, I can determine the line. But I cannot determine the extent of the line, I mean, from where it begins and where it ends. If I want to get the information about where it begins and where it ends, I need to go back to the image and make further analysis. Okay? And see where I have pixels that are having white values and where I have pixels that are having black values. So like this, I can determine where is the start and the end of the line. من الرو الثيتا انا عارف ان هو ده اللاين. اوكي؟ اللاين هو حاجه بهذا الشكل. هو ده اللاين بتاعي. بس from where it starts and where it ends, for example, ممكن يكون اللاين this part. It can be this part, for all of this part. Okay? How can I know this? I need to go back to the original image and see along this line which pixels are white and which pixels are black. Let's assume that the white pixels are only these pixels, okay, from this range up to this range. So this is the line that exists in our original image. Okay? Clear? Any question? Somehow it's difficult to imagine how this transform is working. But the idea here, as we have said before, it starts from this equation, which is the equation of straight line, which is rho is equal to n cosine theta plus n sine theta. Right? And I will start with an image that contains the edges. Okay? And for these edges, this means that the pixels that correspond to edges, which are the white pixels, for each one of these white pixels, I will put the position of m, or the value of m, and the value of n, and I will substitute for the different possible values of theta, from negative 90 up to positive 90, and see the corresponding rho. And for each position of rho and its corresponding theta, I will come to this plane and I will add in its accumulator cell a value of 1. Okay? Another thing that I want you to understand is that any straight line in the original image, it will be represented by a single point in the rho theta plane. Right? Okay? Right. So if we look at the output of the rho transform, and I need to plot it. Here, as you can see, this is a plot of the rho transform, where the horizontal axis here is the theta, and the vertical axis is the rho. Okay? And the intensity of the points here, it represents how many points actually are contributing here. So as it gets brighter, this means that I have more points. Okay? As it gets darker, this means that I have lower number of points. Okay? So here, as you can see from this, I may have different ranges of values for each one of these points. So I need to specify a certain threshold to see or to say that here I have a straight line or not. If the line is short, the value that corresponds to this point, or the point that corresponds to this line in this plot, actually it will have a low value. This means that it will accumulate lower values. But if the line, for example, is longer, but this means that it will become brighter. See? Okay? Clear? Why it become brighter? Because more pixels are contributing to it, so this means that I will have more accumulation here, more increments. Right? are the plots that you will see. طيب, let's go to MATLAB and try to apply this example. Yes. You have in the book, yes, a nice example, this one. It's a nice one. It is the same example that we have seen in the slides. So here, we will start with this image, Control C. This image, actually, it's a mask image. This means that it has just pixels of black and white, okay? And it has inside it a rectangle, which is of white space. Just a moment. Should work now. Yes. Okay? So here, we will read this file, which is called mask1.jpg. I will just show this image just to see what it contains, actually. So it is something like this, okay? It's a black image, as you can see, in which here we have just a white rectangle. So what we are going to do here is that we will just take this part of the image, okay? This small part of the image. So let's do it like this. Here we will take x will be equal. I am just interested in this region. From row 201 to row 400, and from column 401 up to column 600, okay? And we will, so actually we will take just this part. Yes? Yes, الإيمج المفروض إنها بتكون إيمج عادية جدا. مثلا it's an RGB image. We'll convert it to grayscale. Then after that we will apply to it something which is called an edge detector, as we'll see now. Okay? Here we are just taking a simple case. Figure, I am sure. It is just showing us the negative of the image and things like this. Actually, this is an additional step here. It's just showing us the negative of the image. Okay? But you don't need it. Type. Now we will apply a function which is called what? Edge. And this function is able to detect the edges in this image. Okay? So as you can see here, I have my image. Of course, if I need just to give you a small hint. If I will start from an RGB image, what are the steps that I should do? First of all, convert it into grayscale image. Then after that, convert this grayscale image into black and white. Okay? Then after that, this black and white, I will apply on it the edge detector to have the edge image. In our case, in this simple case, actually, I will start directly from here. I will assume that I have reached the stage of the black and white. How can I convert from gray to black and white? Yes, by numbers. How can you do this? Yes, we need to specify a threshold, right? Anything above the threshold will be considered as white, and anything below it will be considered as black. Very simple, right? So here, in our case, we are starting from the black and white, and I will apply the edge detector directly. So here we have this function which is called edge. I will pass to it the image, and then after that I will pass to it the type of the edge detector. Here we have different types of edge detectors. The best one here is called Cannon. And we have other simpler edge detectors which are called Sobel and Prewitt. Okay? We will study them inshallah later when we talk about the image processing of the binary images. Okay? So here we use this Cannon. Okay? And here we use something, a certain factor that we'll see later as well for this Cannon, which is 0.7. Even we don't need this 0.7. Here, if we take it like this, without specifying this value, it will give me an acceptable image as well. So now let's see here. This image Z that is created here, actually it is the edge image. Okay? So we'll try to show it. So as you can see here, we have this edge image. right? Once I have this edge image, now I can pass it to the Who transform. So after having this edge image, I will pass it to the Who transform function in order to have the transformed image in the space of rho and theta. Okay? So here I have the spatial space, which is Mn. It will be transformed into the space of rho and theta. Okay? How can we do this? As well, here in MATLAB, we have the Who transform, which is the implementation of the algorithm that we have just explained here. Okay? So here we have Who, will pass the edge image, which is called Z. It will return three things here. First of all, here it will give me the information, which is the, let's say, this space of rho and theta, which is called H. Okay? T, these are the possible values or the different values of theta that I have applied here, which in this case it will be from negative 90 up to positive 90. And R here, this corresponds to the values of rho that I have obtained when I have substituted these values of theta. Okay? Right? So these are the possible values of rho, and these are the possible value of theta. Why do I need to specify this? Because as you can see, if I will substitute directly in this equation, it will result in some real values that are having fractional part and things like this. So I need to divide my space here into specific locations like this one. Right? So for example, if I have a certain value that comes here or here or here, I need to see or I need to figure out that all of these values within this square, they belong to the same rho and the same theta. Okay? So this actually is something that needs to be specified in order to specify the resolution of the rho and the resolution of the theta. We'll not enter into the details of this part. But what we will see here, we will apply this transform and we will see what will be the result here. So here, take this one, HTR. H here is the result of the Who transform, and T here is the different values of theta, and R here is the value of the rho. So as you can see from here, the image Z, it is 200 by 200 in size, right? What about the sizes of the rho and the theta, or the sizes of R and T? Let's see first of all the size of T here. Size of T here is equal to what? 1 times 180. 180, this corresponds to the range from negative 90 up to positive 90. Right? Rho here is equal 1 times 565. There is a certain formula that we can apply in order to see what will be the different values of rho, what will be the size of rho if I have a certain image with a certain size. Okay? And this information, you can find it in the help documentation of the Who transform in the MATLAB here. So here we go, reference page for Who. We'll find it at the end here, in the section that is related to the algorithms. So here, first of all, he's saying that the expression that we are using is the same expression that we have talked about. Its rho is equal to x multiplied by cosine theta plus y multiplied by sine theta. But here the axes are to be located in this way, okay? Where the x-axis is in the normal direction that we are used to, but the y-axis, its direction of increase is downwards. And here in this case, the origin is the top left corner of the image, okay? And this is the direction of the positive theta. It will be in this case in the clockwise direction, okay? So this is how it is implemented here in MATLAB. Okay? So don't get confused, actually. It is the same concept, okay? But here what will happen is that the direction of the y-axis has been changed. Instead of increasing in this upward direction, it is increasing in the opposite direction. That's it. Okay? And everything else is the same. Now, if we want to get the number of rows or the different values of the for the row, it is equal to 2 multiplied by the CL of D. D here actually is the diagonal distance of the image divided by the resolution, if we have a certain resolution that we can specify, plus 1. Of course, this one has a derivation, okay, but I will not ask you for the derivation, okay, in the exam. Okay, maybe I can give it to you as an assignment, but not in the exam, right? So, and here we have, this is the D, which is the square root of the number of rows squared plus number of columns squared, okay? And this value of row actually, it changes from negative diagonal to positive diagonal, where the value of diagonal is equal to this value, okay? So actually here, we have certain derivation for all of these things. So let's go back to our example. So here we have created the Hu transform. Now let's draw the result of the Hu transform. I want to draw the H. Okay, I want to draw the H. It will be something like the plane that we have just drawn here. So let's take this as a copy, paste it. So it will be something like this. Okay. So as you can see here, these peak values, they correspond to these straight lines. Okay. The other low values here, this cannot be considered as straight lines. I may have non-zero values here, but the value is too low to consider it as a straight line. Okay. So I can specify a certain threshold. Okay. Of course, this value of threshold, it depends on several things. It depends on the application. It depends on the size of the image itself. Yes?
We have like 6 peaks.
We have like 6 peaks, yes.
But for the original picture?
Yes, the problem is that actually this picture, it is not a perfect rectangle, as you can see. Here, we have this corner somehow shifted from this line. This small corner as well is shifted from this line. So all of this will be considered as separate lines, different lines.
But it should be like low value. But
yes, but here this can be considered as considerable values. Here, this value, since you can't see it, when you make it eye, this means that we may have certain values. Let's see here the values of the peaks of the figure that we have here. Of course, here, if I want to get the value of any point on this figure, I will just go to this tool, which is called the data cursor tool, okay? And go to any position you want. For example, here, X, this corresponds to the angle. Y, this corresponds to the row. And Z, this corresponds to the number of pixels here, which is 58. Okay? This is the result of the accumulation. This is the value of the peak. Take care of something. All of these values, you will see that they are having positive values. Okay? Because they are normalized in the MATLAB. Of course, here for the X, which corresponds to the theta, it corresponds to the range from negative 90 up to positive 89. Okay? But it is shifted. So that instead of starting from negative 90, it will start from 1. And instead of ending at 89, it will end at 180. Okay? Same thing can be said here for the Y, which corresponds to the row. For the row, we have said that it will start from negative diagonal to positive diagonal. Here as well, it is shifted in order to have positive values. Right? So, this is one value of the peak. Let's take مثلا this value here. Here I have 139. Here I have 132. 107, 97, and so on. But if I want to see these values in, let's consider more accurately. So let's see here, find, I will use the find function, H greater than, let's say, مثلا 50. Okay, let's put it here between brackets, h of this value. So these are the number of elements and the value of elements that are having values greater than 50. As you can see here, we have several points in the H-plane that are having values greater than 50. Okay? Here, if you look at the image and we try to this one here, actually each one of this line, maybe it is a double line. Okay? Maybe for example here these are 2 rows of white pixels. Okay? So for each one of these rows, actually I will have a new line. That's why here you will find that the values may appear sometimes in pairs. Okay? So here if we go back to these values, actually I don't have all of these straight lines in my figure. Okay? But I may have white lines that are in parallel to each other. Okay? And they appear for the naked eye as if it is a single line. But it consists of, let's say, مثلا 3 or 4 lines that are in parallel to each other. And they are contiguous to each other as well. That's why here we have lots of values that are greater than 50. Clear? So now, in this next chapter, we will start to see some more interesting applications of this transform. In this chapter, actually, it is not just about the transforms, but it is about, in general, how can we design a filter, either in the spatial domain or in the frequency domain. Okay? So this means that for the same image, I can either filter it in the spatial domain. In this case, I don't need to transform it into the frequency domain. Or I can transform the filter to the frequency domain and I apply the filter in the frequency. Okay? Then after applying the filter, I can make the inverse transform again to the spatial domain. So here in this chapter, we will see these 2 types of filters. So the topics that we'll see here first of all, we'll start with the spatial domain filter design. This means that these filters can be applied directly on the image as is without any transformation. So here we will have introduced the convolution operation. This is the main operation that we will use in order to apply the filter on. And then after that, here we'll introduce these 4 types of filters. We have the averaging or mean filter, we have the median filter, we have the Gaussian smoothing, and the conservative smoothing. And we'll see what are the differences between them. Then after finishing with the spatial domain filter design, we will see the frequency-based filter design. Okay? And at the end here, we'll have some MATLAB examples. Okay? So let's start by the introduction. Here we say that one of the main things that we may need to do in image processing is filtering. Okay? So here we say that image processing filters are mainly used to suppress. It's a filter. So this means that it will pass certain things and it will block other things from passing. Okay? So here it can suppress either high frequencies in the image. Okay? So in this case we are making smoothing of this image, or we are suppressing the low frequencies. Okay? And in this case this means that either I want to enhance the image, this means that I want to increase the contrast in this image, or I want to detect the edges. Here I'm interested in knowing when can I find the big changes in the pixels, okay? So in this case I will allow this to be emphasized on, while I want to remove the low frequency components, okay? So here we have the low pass filter. Low pass filter, this means that it will allow just the low frequencies to pass. So this one is used for smoothing and for noise removal as well. This means that it will remove the high frequencies and it will keep the low frequencies. Or I have a high pass filter. So in this case, I am interested in the high frequency components. And this can be used in order to enhance the image by increasing its contrast, or by detecting the edges, like for example the one that we have used with Kami. if you remember the one that we have seen in the previous example. Okay? So here we say that, in general, the image can be filtered in either the frequency or in the spatial domain. Here it depends on the easiness and the, let's say, the smoothness of doing this kind of operation. In both cases, we say that we need to replace some of the pixels with approximate pixels that can improve the overall visualization of the image. Okay? You're improving the visualization. Here it depends on what I want to do, whether smoothing or edge detection. Right? So here we say that in case of spatial domain filtering, the filtering operation is done using a convolution. So in this case, I will have a filter kernel, we call it a filter kernel, that will be applied on the different pixels of this image. Of course, here the size of the kernel is different from the size of the image. I may have an image of any size, but the kernel can have a size of 3 by 3 or 5 by 5. And this kernel, it will be applied on the pixel of the images, pixel by pixel. Okay? Right? In the frequency domain, on the other hand, the image is first transformed into the frequency domain using the fast Fourier transform, for example, and then we will apply the appropriate filtering is applied. Here, the filtering operation is to be done by multiplication, direct multiplication. Okay? And in this case, the size of the filter will be equal to the size of the image itself. Okay? It will be a single multiplication operation. While here, I have a kernel that needs to be applied on the different pixels that exist in the image, in the case of the spatial domain. So here in this case, the size of the spatial domain, actually I don't have any relationship between the size of the image and the filter kernel. The filter kernel, it should be some odd number by an odd number. It's a square. So it can be either 3 by 3, 5 by 5, 7 by 7. It depends. Okay? And the image, of course, it can be any size, n by n. Okay? But here in the frequency domain, if the image size is n by n, the kernel itself, the filter kernel, or the filter itself should be of the same size, which is m by n. And we'll see how this will happen. Okay? And here we have said that the filtering is applied in the spatial domain using convolution, but it is applied in the frequency domain using what? Multiplication. Okay? Which is the relationship between convolution and multiplication in both domains. Okay? So here we say that in the spatial domain filter, assuming that my image is F and my filter is H, so if I make a convolution between them, the resulting image G will be the filtered image. Okay? So here we say that the spatial filter design involves convolving the input image F with the filter function H. Okay? And the mathematical operation, of course, is identical to the multiplication in the frequency space. It is equivalent to the multiplication in the frequency space. Okay? Type. Now let's see the convolution operation itself, how it will be performed. So here I am assuming that I have a filter of size n by m, right? And my image is F. Okay, it has a certain size, right? And here we will see that for each point in the, let's say, in the resulting image, it will be obtained using this expression. Where here we find that x and y, this is the position that corresponds to m and n after filtering, right? So here what will happen is that, as you know, how can I describe the convolution? What is the operation that needs to be done in the convolution? Shift, multiply, add, right? So in this case I need to make a shifting. The shifting is done here. If you notice here the values, or let's say the parameters, here I have x and y, and here I have n minus x and n minus y. Okay? Then after that I will make the multiplication, then after that here I have the summation. Okay? So in this expression I have all of the three, let's say, steps that are related to the convolution. So here we say that discrete convolution is composed of three operations. In discrete, of course, the things are much more easier than in the case of continuous, because in continuous I need to make integration and things like this. Here it is just shift, and the shifting here I don't need to make shifting, because the kernel in most of the cases here is symmetric. So whether I will shift it or not, it will give me the same result. Okay? So I need to make multiplication and addition. Okay? So here we say that shift, multiply, and summation, where we shift the kernel over the image and multiply its value with the corresponding pixel values of the image, and take the sum of this multiplication. So here we need to make a shift, we need to make a multiply, and then after that we need to get the summation.
So how the image is symmetry?
Yes, here for this kind of, let's say, مثلا here for the averaging. Averaging, it will be something like this. I will have 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay? And all of this actually is to be multiplied by 1 over 9. If I want to make an averaging of 9 pixels. Okay? If I want to make, for example, sharpening, it will be something like this. Here I may have, let's say, here 9, minus 1, 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 minus 1. And this, after that, will be multiplied by my image. So as you can see, this is, in general, this one is for smoothing, this one is for sharpening. And in both cases, as you can see here, the image is symmetric around the center point. See what I mean? So here, in all of the cases, the kernel that we are using in the spatial domain is square. It is m by m. And m, in all of the cases, is an odd value. Okay? Either 3 by 3, 5 by 5, 7 by 7, and so on. Okay? Do you have any question here? Okay. Let's look at the types of filters. The type of filters that we will see in the spatial domain. In the spatial domain, again, here I don't need to make any transformation. I will make convolution directly with the filter. We have the averaging or mean filter. We have the median filter. We have the Gaussian smoothing and the conservative smoothing. Okay? So, here, as you can see, here is giving us some idea or some examples of the kernels that we use. So here in part A, actually this is the 3 by 3 averaging filter kernel. It's something like this. It's 1, 1, 1, 1, 1, 1, 1, 9 ones, and all of these are to be divided by 9. Okay? So how can I get the smoothing? How can I get the average here? Okay? Now I will get this kernel, and I will put it coinciding, for example, on the pixel xy. Okay, the pixel at position xy. Okay? And the kernel, actually, it will be applied on this part. So here in this case, I will have 1, 1, 1, 1, 1, 1, 1, and all of this is to be divided by 9. The position of this pixel here, it will be x minus 1. Y minus 1. This one, it is x minus 1. Y. This one, it is x minus 1. Y plus 1. Right? This one is x. Y minus 1. This one is x. Y plus 1. And so on. X plus 1. Y minus 1. X plus 1. Y. X plus 1. Y plus 1. Okay? Right? So here what will happen is that I will get this 9 values and I will coincide them, and each 2 values actually corresponding to each other will be multiplied, and the result of these 9 multiplications will be summed up together. Okay? So if I will apply this filter, which consists of 9 ones, like this ones. Yes? That position at the pixel, this is pixel xy, okay? And I want to apply this kernel on it. So in this case, since the size of the kernel here, it is 3 by 3, so I will see the neighborhood that has the size of 3 by 3 about this pixel. So these are the coordinates. This is the number of rows, this is the number of columns for each one of these pixels. So if this is row x, this will be row x minus 1, this is x minus x plus 1. This is column y minus 1, column y plus 1. Okay? So I will get this kernel, and I will put it coinciding on this part. So here the center value here will be coinciding over this pixel. And then after that, this top left value of the kernel will be multiplied by the top left value of this neighborhood. And here this value as well will be multiplied by this value. Okay? And the center value here will be multiplied by the center value. And after that, after multiplying all of these 9 positions together, I will add them up. So what will be the result here? If I will apply this specific kernel, it will be an average. As if I am multiplying, for example, I'm adding all of these values together, all of these 9 values, and then after that I'm dividing them by 9. Right? Okay? So this will have an averaging effect. Also, we have some other type of kernels, which is called the median kernel, as we'll see later. And also we have here a 2-dimensional Gaussian distribution. Here, instead of having all of these values will have equal values, like here in part D, I may have a distribution like this one. So that the central part here will have the maximum effect, and as I go further from this central part, the effect will start to reduce. Okay? This is called the Gaussian distribution. This as well can be used in smoothing as well. Okay? So we'll see all of these things. So now here, for the averaging or mean filter, we say that it's a method of smoothing images, let's say reducing the amount of intensity variation between one pixel and the next. Okay? So actually if we apply this thing, actually this means that I will make the average of the pixel with respect to its neighboring pixels, including the pixel itself. Right. So this is the idea. Let's see an example of the effect of this averaging. So you will say that when we make this kind of averaging, this means that I am making some sort of smoothing of the values that I have in this image. Okay? In other words, we can say, for example, if I have an abrupt changes between the neighboring pixels, here, for example, I have 100, here I have 20, here I have 10, here I have 200, here I have 300, and so on. When I add all of these values and divide it by 9, so this means that all of the differentiations, or let's say these abrupt changes, will be smoothed out. As if I am removing the high frequency component. And this is the effect of averaging, actually. Okay? But the problem here is the following. Let's say, مثلا, here let's look at this example. Here I have in image A, this is a noisy image. Okay? Here the noise have been added to the image using Gaussian noise distribution. Okay? And this image B, this is the filtered image using the average. So in this case, as you can see, I have some sort of smoothing. Maybe it is not that clear here. I have some sort of smoothing, but the noise was not removed totally. Okay? But it was smooth. It was smoothed out. Okay? Here I have another image, but here we have added another type of noise, which is called salt and pepper. So using the specific pixels, and I will add to it a certain, for example, a peak value, or I will subtract from it a certain value. Okay? And this is the effect after applying the average or the mean filter that we have. Okay? Right? So here for this averaging or mean filter, we say that we have two problems. We say that a single pixel with a very unrepresentative value can significantly affect the mean value of all pixels in its neighborhood. What is the meaning of this? For example, assume that I have in my 3x3 neighborhood of the image, I have, for example, this value, which is 20, 30, 20, 30, something like this, 20, 35, 30, 35, let's say 30 here. And this pixel is noisy, and it has the value 150. Okay? If I will add this pixel and get the average, and replace this pixel by the result of the average, of course this value actually it will be changed a lot. It may jump, for example, to 20 up to 40, which is double the value. Okay? So this is one of the problems here. A single pixel with a very unrepresentative value can significantly affect the mean value of all pixels in its neighborhood. Another thing here, we say that when the filter neighborhood straddles an edge, you know what's the meaning of straddling an edge? This means that I have here in my normal image, I have an edge like this one. Let's say, here I have the values between 20 and 30, and now here I have the values of something like this. So here I have an edge, right? When I apply the averaging operation, what will happen is that this edge actually will start to disappear. Okay? So here we say that when the filter neighborhood straddles or crosses, we say, crosses an edge, the filter will interpolate new values for the pixels on the edge, so will blur that edge. What's the meaning of blurring the edge? This means that the edge will start to be hazy. Okay, instead of having a clear distinction or a clear contrast, the contrast will be reduced. Okay? And this may be a problem if sharp edges are required from the output. Okay? So these are the two problems of the averaging or mean filter. So, what is the solution here? Use another filter, exactly. So we will use the next filter, which is called the median filter. Median filter here, it has better results. Here we say that the median filter is normally used to reduce noise in an image. Somewhat like the mean filter, so it has the same purpose, it will reduce the noise. However, it often does a better job. How? Here we say that both of the problems related to the mean filter are resolved by the median filter. If you remember, the two problems that are related to the average filter or the mean filter is that a single pixel with unrepresentative value will affect all of its neighboring pixels. And if I have an edge, this edge will be blurred. How this will be solved in the median? Let's look at this figure here. Okay? The median filter will be something like this. Actually, here I don't have a specific kernel for the median filter. I will look for this neighborhood of 3 by 3 pixels. I have the value of these pixels. I will sort them. I will order this value of the pixels, and I will take the median. Okay? The pixel in the middle. So after sorting this one, since this is 9, so I will take the 5th value that appeared after sorting these values of pixels. So here, for example, if I have these values, after sorting them, it will be 100, 100, 101, 102, 103. So this pixel that appeared at the center, it will be replaced by the median value of these 9 pixels. Okay? But let's see here what will be the advantage of doing such thing. So here we say that the median filter considers each pixel in the neighborhood in the image and replaces it with the median of the values. And the median is calculated by first sorting the pixel values from the surrounding neighborhood into numerical order, then replacing the pixel with the middle pixel value. The median, yes. From the, and here you will have this 9 values. First of all, sort them in an ascending order and take the middle value for this neighborhood of 3 by 3. Okay? Right? So here we'll take the middle value, which is called the median. So here we say the median filter is very desirable for removing salt and pepper noise. Let's look here at the results. So this is the noisy image with the Gaussian noise. If we apply the median filter, we'll have something like this. Actually, it is not that great. But if we apply it on the salt and pepper, this is the result of the filtering. Okay? It is almost like the original one. It is almost like the original one. So here we can summarize the advantages and disadvantages in this slide as follows. We say that the median is a more robust average than the mean. So a single very unrepresentative pixel actually in the neighborhood, it will be excluded. صح? Any value that is unrepresentative, either it will be the least value or the maximum value, so I will not use it. Okay, so it will be removed. Right? It will not be considered, and it will not affect the image that we have. And since the median value must actually be a value of one of the pixels in the neighborhood, so this means that it will not change greatly in the original image. If I have, for example, let's say an edge, the edge will remain there. Okay? The edge will remain there. And at the same time, if I have an unrepresentative value, this unrepresentative value will be excluded. It will be considered something that's called what? Outlier. Either it is the minimum value, it is very low, or it is very high. So it will be removed. It will not be considered. The only disadvantage here that we have, if we compare it with the average filter, is that here the computation complexity. Here, first of all, I need to sort the values, then after that get the median. If I will compare it with the average, of course, it is straightforward. Just multiply and add, and that's it. Okay? So if I will make, for example, the operation of the sorting, this operation of sorting, it may be in the order of n squared. Okay? While here, for example, if we consider the complexity of the multiplication, it will not exceed n. Right? For the average filter. Right. Do you have any question here? Okay. Right. So we'll stop here.